Okay. This is a video that was requested by a few students in regards to a formula sheet slash key concept review in AP statistics. The test being next week. I figured I'd put everything down into a sheet of paper. I don't know if it's going to be a single sheet of paper or multiple sheets of paper, but this is what I'm going to do. I am going to scan the pages after the fact and make them available in a PDF, which I will send to my students and also include in the description when the time is appropriate. So here we go. So first of all, going back to very early on, we had this concept of IQR, interquartile range. When you are given a set of data, however many data points you have, if you list them from least to greatest, clearly you can identify the minimum and the maximum, and the middle value being the median. If there are two middle values, take the average. But if you take the lower 50% and find the middle point, that would be Q1. If you take the upper 50% and find the middle point, that would be Q3. The interquartile range would be the subtraction of the two. The reason why we needed that was to determine, given a set of data, whether or not a certain data point was considered an outlier. There's a couple different ways to identify outliers, which I'm going to get into. But if you were to be an outlier, to be considered an outlier, a point is outside the range, parentheses, Q1 minus 1.5 IQR, comma, Q3 plus 1.5 IQR. If you were a data point outside that range, you would be considered to be an outlier. Now, that is slightly different from that of being considered unusually high or unusually low. It's a similar concept, and I guess they're somewhat interchangeable, but the unusually high, unusually low concept had to do with z-scores. And if you were dealing with z-scores, then you had to be normally distributed or nearly normal, which is fine. But this is for, quote, unusual, if I can spell, unusually high / low, end quote, is when you are more than 2 standard deviations away from the mean. Then you would be considered unusually high or unusually low. You could also potentially find probability using the normal distribution. The general concept for normal CDF function in your calculator. I'll put lower limit, upper limit, mu and sigma. So given a set of data with a mean and a standard deviation, or an accepted population mean and population standard deviation, you could find something along the lines of, and I'll just make up an example here. Let's just say that you had a mu at 120 with a standard deviation of, I don't know, 10 or some junk like that. If this were the case, then let's say I wanted to find out, or what are the chances, or what is the probability of getting a data point that is 130 or higher, something along those lines. So that would be something like normal CDF 130, comma, some big number, comma 120 for your mean, comma 10 for standard deviation. I don't know, just for the sake of argument. And that would give you approximately a 0.159 chance, 15.9% chance. Now, again, standard deviation, just to kind of talk a little bit about that. We were given a certain formula for calculating standard deviation, but I don't know any test that would force you to calculate the standard deviation by hand. But it is good to know the structure of standard deviation, which allows you to understand its behavior and definition. It is similar to that of average deviation away from the mean. I just need to type a comment real quick. There we go. Boom. Okay, good, good, and good. Let's get rid of that. Let's go back to here. All right, and we're back. Now, again, standard deviation being average deviation away from the mean. One side note that I'm going to get back to in a little bit is just the idea that standard deviation squared would get you this concept called variance, which doesn't come into play at this moment, but will come into play a bit later on. Basically, you remove the square root, and it becomes this concept known as variance, which we will get into in a little bit. In terms of being unusually high and usually low, I mentioned before Z-scores. Z-scores being the number of standard deviations above or below the mean that a data point could potentially be. If you're talking about Z-scores, the typical way that they can be calculated, data point minus mu over sigma would knock out that Z-score. So if you were somebody in that scenario, example, with a mu at 120 and a sigma at 10, and you were somebody at a data point of 130, your Z-score would be 1 because you would lie 1 standard deviation above the mean. If you were to work backwards, that would come into play with the concept of inverse norm. Inverse norm would spit out a Z-score given the percentile that you type in. So for example, inverse norm of 0.75, just see what it does, gets you approximately 0.67, which would be the Z-score at the 75th percentile. Remember the concept of the normal curve. The 50th percentile is right in the middle. The 75th percentile, that would be a Z-score right about here. That would be the 75th percentile. Each dotted line represents 1 standard deviation above or down here below the mean, of course. Now, just for the sake of argument, inverse norm percentile mu sigma, if you were to also type in those values as well, and I'll show that right here, inverse norm 0.75 comma 130, no, mu is 120, 120 comma 10, it spits out, for this example, 126.74. So the 75th percentile would have a value of 126.74. If you just leave inverse norm with the percentile, it spits out the Z-score. If you do inverse norm with these extra data points, then it'll spit out the value at that particular percentile. let's see, just one more I'll do a few more things with normal curve before I go into linear regression. But if we were talking about the empirical rule, basically if you have data that is normally distributed between -1 and +1 standard deviations, you would have 68% of the data. Between these two, you would have 95%, -2 to +2. And from +3 to -3, you would have 99.7% of the data. Now, this is the empirical rule. These numbers are approximate. These are not the exact values. But generally speaking, if you were between whatever standard deviation, -1 to +1, you would have that percentage of the data approximately. That allows you, for example, if you wanted to find the percent of the data in this example, which I had this at like let's turn this into a 120, a 130, and a 140. If you wanted to find the percentage of the data that was between 130 and 140, you could either do something along the lines of normal CDF 1 to 2, which would give you the Z-scores, which I'll show you on the calculator in a moment. Or you could do normal CDF 130, 140, 120, 10 in order to include the mu and standard deviation. Normal CDF 1 to 2 spits out that percentage. Normal CDF 130, 140, 120, 10 spits out obviously that exact same probability, that chance. You could express this as the percent of the population, 0.1359, the percent of the population that is between 130 and 140, the percent of the population that is between 1 and 2 standard deviations, or you could describe it as if you picked a person at random, a single person at random, then this would be the chance that they would lie between those two data points, 130 and 140. There's multiple ways of expressing this, but keep in mind it would have to be a singular person, and they would have to give you the population mu and standard deviation to get that thing done. Let's talk about linear regression. Again, all these pages will be made available to you. I'm going to scan them in after the fact. Linear regression, we talked about R, the correlation coefficient. The formula of which, you know, it's helpful to see it. But it would basically be you find the z-score of the x times the z-score of the y for every single data point in the set, multiply them together, you get all these individual multiplications, add them all up, divided by 1 less than the sample size, and that would give you the approximate value of R, which is the correlation coefficient, which describes the strength of the correlation. R is typically measured between 1 and -1, 1 and -1 being perfect correlations. The sign on the R would determine whether or not the slope of the line of best fit would be positive or negative. Obviously, an R with 0 would be no correlation whatsoever. But there are formulas on the formula sheet that they tend to give you. They do tend to give you y hat is equal to b sub 0 plus b sub 1x, which is nothing more than your y equals mx plus b. Your m being your slope, your b sub 1. Now, typically we say change of y over change of x, but in this case, it's standard deviation of y over standard deviation of x times r. Should put times there. There we go. And that would give you the value of your slope. That's how the calculator does it. And your b sub 0, your y-intercept, would be equal to y bar minus b sub 1 x bar, or the average of y minus your slope times the average of x. Of course, your calculator can get this thing done for you. If you type in your data into L1 and L2 and then run a linear regression, it will do it for you. Just make sure that you have your diagnostics on if you have a TI graphing calculator. You got to make sure your diagnostics are on, otherwise it will not give you the value of R or R squared. Keep in mind the R squared value, typically given to you as a percentage, represents, and again, I don't have any context for you because I haven't defined what X and Y are for this particular problem, but your R squared would typically be the percent of the variation of Y that is accounted for by the linear model or the regression model done on X. Whatever context you needed to attribute to that, is exactly what it is. So anyway, now R being the correlation coefficient, R squared, I should write this down. R is the correlation coefficient. Just to keep in mind, they may not use R. Most of the time they do. And R squared it goes by a few different names, but you could call it the coefficient of determination. Again, just in case they don't actually tell you R squared, but instead they just give you those vague terms. That would be acceptable. Let's see. Let's jump into, well, actually, no, let me write a couple of things. I was going to jump to linear regression, not linear regression, probability, but I'll go to that in a minute. Just keep in mind, if you do have your diagnostics on, your residuals will be calculated. Residuals are observed data points minus the predicted data points, typically the Y values. If you want to know whether or not a linear model is appropriate, you look at the residual graph. The residual graph should be scattered. There should not be a pattern. If there is a pattern, some kind of form, then a linear model would not be appropriate. So please keep that in mind. Let's jump to probability. Probability, start with some of the more basic formulas. They give it to you like this for the most part, but this formula is for OR, the probability of A or B. This would be OR. This symbol representing AND, which we'll talk about in a little bit. Keep in mind the general concept behind whether or not they are mutually exclusive. If the probability of A and B is equal to 0, then A and B are what they call mutually exclusive, meaning there's no overlap. They have nothing in common. If you were to draw a Venn diagram, there would be nothing in the overlap, nothing in the middle section if they were mutually exclusive, which means that the events A and B cannot happen at the exact same time. If you're talking about the probability of A and B, which is the word and, technically there are two different formulas. This would be if the events are independent, and this would be if the events are dependent. The general idea being if A and B are independent, then the probability of B given A should be approximately equal to the probability of A. If they, I'm sorry, what am I talking about? The probability of B, because then the given event would not matter. If they are independent, then this relationship would hold true. If this relationship does not hold true, the best you can say is they are not independent. You would need further evidence in order to show that they are dependent on each other, which I mean, it is entirely possible to rationalize the fact that two events are dependent on each other. If you had a bag of marbles and you took one marble out and then you did not put that marble back, then your next pick would be dependent on the previous one. Clearly, that one verbally can be taken care of. But this definition, you would just show that the two events are not independent. Just write the word "and" here as well. You were also given this formula, which when I eventually do my review video on probability, I'm going to expand upon probability a lot. But this formula is very helpful if you have to find the probability of B given A. Then it would be this calculation. Remember, you always divide by the probability of the given event. Finally, just as an aside, the probability of A is equal to 1 minus the probability of A complement, just being that if the probability of A is 75%, then the probability of not A, or the complement of A, would be 25%, for example. Sometimes they do throw stuff like that at you. Let's talk about expected value. There's a little bit more in terms of probability, but in the order of the book, we went to expected value next. Expected value is they give you some kind of a model where different events have a different chance of happening, and you can calculate expected value by doing the following calculation. There we go. Where X would be the individual events that could happen, like what would be the result of those individual events, the value of a dice roll, or the amount of money that you would earn from, I don't know, from whatever the game is, I guess. And then you would multiply by the probability of that event happening. You would get all these different multiplications, add them all up, and that would be the expected value. Or if the game or the event happened a numerous number of times, then the average winnings or the average result would be the expected value. And this is what we get. Now, standard deviation, I'm going to do an example of this in a moment. Standard deviation, sigma again, would be the following calculation, where it would be the deviation squared times the probability of that event happening, add them all up, giant square root. For example, if, and I'm going to have to make this one up, let's say that you win $0 50% of the time, you win $5 a fourth of the time, and you win $10 a fourth of the time. I'm just going to keep it simple. Obviously, those are all the possible outcomes because they add up to 100%. This would be X. This would be the probability of X. You could run through these calculations, get expected value, get standard deviation. For the most part, they're fine with you calculating expected value by hand. They usually don't have you calculate standard deviation by hand. But if you just wanted to go straight to the graphing calculator, you could do it in the following fashion. In the first column, notice that I put in the values, the resulting values of the events. In the right column, I put the probability of that particular event happening. You could run a 1-var stat, but make sure you do L1, L2, and it would spit out an expected value of 3.75, which actually is mu in this case. There we go. And a sigma of 4.15, approximately, I should say. So on average, people would expect to win $3.75 in the long run if they played it a number of times, or if they took the average of like a couple hundred people playing this game with a standard deviation of $4.15. It's probably so large because of the $10 range. Because obviously, standard deviation, you can't go below 0, but I digress. Now, in terms of expected value, if you had two different events, let's say like X and Y, and you wanted to find the combination thereof, where you were like, okay, I have two events, what's the expected value of these two independent events if I added them together? And individually, you just find the expected value as such. You want to find the difference, you subtract them. If there's a multiple happening or scalar happening where you have to multiply one of the events by 5, yeah, the expected value is multiplied by 5. Everything with expected value, any change in the calculations happens the way that you want it. But with standard deviation, if you were to combine two random variables with standard deviation, can't do it. You need to convert to variance. That's the thing we talked about earlier. Then perform the appropriate calculation. Perform appropriate calculation, and then convert back to standard deviation. Now, just for the sake of argument with variance, if you are adding or subtracting two independent random variables, it doesn't matter if you're adding or if you're subtracting them. Not a typo. You add them. And we went into great detail on that and the reasons as to why when we originally covered the concepts of variance. But again, I'll go into more details when I eventually get into my longer video on probability. Let's talk a little bit more about probability in regards to geometric and binomial distributions. Now, a geometric distribution in general, and I'm just kind of key phrases, waiting for a first success. Typically with geometric distributions, we're waiting for a first success. So if the chance of some event happening, or if the chance of me winning a certain game is like 25%, let's say, what are the chances that I would have to wait until my 5th time playing the game in order to get that first victory, let's say? And be like, well, I lost the first one, second one, third one, and fourth one, and then finally won, and it would be approximately 8% chance, because I would have to lose those first 4 times and then finally win the 5th time. Of course, with by PDF, which I'm going to write those stuff down in a little bit, you could also write it like, well, I have a 25% chance of winning on my 5th try. And you can see that calculation right there. Winning on or before my 5th try would be a little bit more complicated to type out by hand. You would have to calculate winning on the 1st or the 2nd or the 3rd or the 4th or the 5th and then add them all up. Or winning on my 5th try or sooner, there's approximately a 76% chance of that happening. Let's go into a little bit more detail. On average, the trial that I should win on, if you take 1 divided by the probability of success, that would give you the trial that you are expected to win on. So for example, 1 divided by 0.25, I should, on average, I should win by the 4th trial. Standard deviation. Now, standard deviation for geometric is not typically used. I have not seen that many things ever using the standard deviation of a geometric distribution. But just in case, not typically used. The probability model is written out like this: Q, which is the probability of failure, to the x minus 1 power times p. That would give you the approximate probability. But of course, we use Geomet PDF or CDF, which in order you'd have to type in the probability of success, comma, the trial that you're trying to get the success on. PDF is, I should put success. Yeah. success on exactly, I can spell the word exactly today, exactly xth trial. CDF would be success on xth trial or sooner. CDF is cumulative. PDF is just the regular probability density function. CDF is cumulative. So keep that in mind. Let's talk about a binomial. Let's see if I can fit this on the bottom here. A binomial would be getting X successes in N trials. So typically there's a finite number of trials that you are dealing with in terms of binomial. N times P would give you the average. So for example, if I'm playing this game that I believe I have a 25% chance of winning, if I play it 10 times, then I expect to win about 2.5 times, or I expect to have 2.5 successes. Standard deviation, which is much more helpful, NPQ, that will come in handy a little bit later on, especially with what the binomial turns into, which details are coming soon, of course. Sorry. I'm hearing something in the backyard. What is... Oh, look at that. I say them. And yeah. Sorry. Just for the sake of argument, for those who eventually listen to this, I live with my backyard facing a golf course, and one of my associates happened to be golfing and yelling into the backyard. Back to this. Okay. The binomial model. Now, the probability of calculating these things, which is a lot easier on the calculator, has the following formula. Now, this formula is not typically used. The combination of nx, which would be n factorial over x factorial times n minus x factorial, that's not something we typically use in AP Stat. We typically stick to whatever calculation we need here. This formula would typically need to be identified when it comes to a multiple choice question. Of course, for the 2020 test, there will be no multiple choice. So I'm almost certain you won't have to worry about that. Now, in terms of binomial, binom, PDF, the order in which you would type it into the calculator would be NPX, N being the number of trials that you're performing, P being the probability of success, X being the number of successes that you're looking to get. PDF would be X successes. CDF would be X successes or less. There are some weird things to go along with that, but of course I'll deal with those details in a future video. Now, I need paper. What does this eventually turn into? There is a property which indicates that as the number of trials increase, as number of trials increase, a binomial, and I'll show you an example of this, approaches normality. It approaches a normal distribution. And for the normal distribution and the normal CDF, if you have a binomial situation, we're going to do lower limit, upper limit. Sorry, it wouldn't be mu. I'm getting distracted by what's going on out there. Yeah, getting totally distracted. NP which would be the mu, or the mean of the average of the binomial, and then the standard deviation would be the square root of NPQ. Now, for an example, let's just say, and I'm going to keep going with that 25% example. If I have a 25% chance of playing a game, and let's just say I play that game 200 times. So I play the game 200 times. And I'm looking to get, I don't know, half or better. So we're going to say, half, which would be 100 wins or better, for example. Now, if I was going to be doing binomial, I'd do 1 minus binom C df 200, 0.25, 99, which if I did it with the 99, that would give me 99 or less wins. If I did 1 minus, it would give me the 100 or more. Again, more details coming in the probability. 1 minus binom, the other way. CDF 200, 0.25, 99. And, well, I should probably pick a different number. If I'm getting that as an answer, I definitely need to pick a different number if I want to get something a little bit more appropriate. Let's go 30. We'll go 30 wins or better. I want to get an answer. I want to get a number that can actually see there. So I'm doing that many or better. Then I would do 29 or less there. Let's change that here. Okay, I could deal with that. Yeah. So if I'm playing 200 times, I'm expecting to get 50 wins on average. But if I'm looking 30 wins or better, then it looks like approximately 0.99979. Let's look what the normal distribution does. If I'm going to be doing normal CDF, it would be 30 wins or better times, or comma, I should say, 200 times 0.25, which what is, I did that's 50. I'm expecting 50 wins times the square root of NPQ, which is 6.123. Find a normal CDF of 30, comma, big number, comma, 50, comma, that answer. Yeah, gives me approximately 0.99945. Again, just that general idea. As the number of trials increase for a binomial, it approaches normality, and you can technically use a normal CDF as long as the number of trials is large enough, is what they typically refer to, and that would be acceptable. Then we eventually got into sampling distributions. With sampling distributions, it talked about a sample being taken. And with that sample being taken, there are certain things that we can adjust in order to do certain calculations. So, for an exampled difference, just to show the difference between a sample distribution and a regular normal distribution, if I go back to that original example I did where I had like some mu at 120 and a standard deviation at 10, and I said, okay, what are the chances that a person falls between, let's just do 130 or better. Let's just say 130 or better, big number, with a mean of 120 and standard deviation of 10. I already forgot what that answer was. Let's just do it here real quick. 130, comma, big number, comma, 120, comma, 10. It spits out approximately 0.159. But that's just the chance of that happening to one person. If you had only 100 people, let's say out of a sample size of 100, just 100 people, not the population, let's say a sample size of 100, sampling distribution, what are the chances that of those 100 people, I get an average of 130 or better? Now, I'm going to do that with the sampling distribution. I would have to change my standard deviation, which I'm going to give the formula for that on the next page. But it would be sigma over the square root of n. I would have to adjust my standard deviation for the sample. And it should separate these two. So if I was to do this calculation again, but instead dividing by the square root of 100, that gives me a tiny number, 7.8 times 10 to the negative 24th power, which is approximately 0. The idea being that if I'm just looking at one person being 130 or more, the chances of that happening are almost 16%. But if I'm looking at an average of 100 people taken from a sample, a mean of 100 people being 130 or better, the chances of that happening are almost nothing. It's a big difference between the two with sampling distributions. If you are talking sampling distributions, the mu of whatever your assumed mu of the sample would still be the population mu, but the standard deviation of the sample would be sigma over the square root of n. And that's if you're dealing with quantitative data. If you were dealing with categorical data, then I'm dealing with p hat this time. Your assumed average would still be the population p, but your standard deviation of p hat would be the square root pq over n. Notice the n being in the bottom of the fraction underneath the square root. Yeah, and it would basically be the same thing as before. Normal CDF, lower limit, upper limit, mu, and I'll just do it for this one, but then it's sigma over the square root of n. We have to take that into account. For sampling distributions. That led into the fundamental theorem of statistics. Which is also known as the central limit theorem. Just basically that a distribution of sample means, which before with that sample size of 100, that was just one example of that happening, but a distribution of sample means becomes more and more normal as that sample size grows larger. And again, with a binomial, it kind of falls into the same realm of a binomial. With a binomial, as the sample size grows larger, then the binomial approaches that of a normal distribution. And again, I'll probably do another video. Well, if I have time, we'll see. Another video on sampling distributions, but I want to make sure I hit the rest of the information before this video gets incredibly too long, which it already is. Let's talk about confidence intervals. In general, on the formula sheet, they give you something like this. Statistic plus or minus the critical value times, now they say like the standard deviation of the statistic, which is typically your standard error. Not necessarily your standard deviation, but it's your altered standard deviation. We'll get into those details. There were three main confidence intervals that you could do in the calculator. One of them being p hat plus or minus Z* times p hat q hat over n, giant square root around it. If you're dealing with proportions, of course, or x bar plus or minus Z* times the population standard deviation over n. Now, if you have the population standard deviation, you would still be doing z. I'm going to do a little chart on my next page. Or if you don't have the population standard deviation, then you would have a sample standard deviation in which you can or you would have to use T-star instead. I did a video on how to do inverse T without actually having it on your calculator. You should check out that video when the time's appropriate. I talk a little bit more in detail about this particular part of the confidence intervals. So keep that in mind. Let me give you that chart, which is oh so helpful as a reminder. That chart being, well, what type of data do you have? Is the data you have quantitative, or is it categorical? If it's quantitative, it makes sense to take an average. If it's categorical, you're dealing with proportions. If you're dealing with proportions, you are going to be dealing with the Z, no matter what. It doesn't matter if it's one sample, two sample, doesn't matter. You're doing Z. For quantitative, it depended on whether or not you have the population standard deviation or you don't have the population standard deviation. If you have the population standard deviation, you would be doing Z. If you don't have the population standard deviation, you'd be doing T. This is the main distinction between the two. The main distinction between the two. Just as a reminder, this is for hypothesis test or for intervals, which I'm going to talk a little bit more about. But if you are running a test, you have an assumed mean. If you are doing an interval, you are trying to capture the true mean. Just note the difference between the two. If you are running a test, there is an assumed mean that you're dealing with. That mean could be proportions. That mean could be quantitative means. But for an interval, you are trying to capture the true mean. This could spell a bit of an issue when you're dealing with pooling the proportions or not. If you have the graphing calculator, most of that is already taken care of. Assumed mean for the hypothesis, it'd be like the null hypothesis with h sub 0, mu is equal to this, and you assume that for the rest of the problem until proven otherwise. You either reject or fail to reject. For the interval, you are only a certain percentage confident that you have captured the true proportion or true mean or whatever it is that you're dealing with. Let's see here. Let me go back to the Z-star. For Z-star, let's just say that you were, I'm going to come up with something weird, 88%. Let's just say 88% confident, which again, yeah, there's not that many things that ever have you do 88%. It's usually like 90%, 95%, etc. But let's just say you were 88% confident. Now, if you're 88% confident, that means that you're not capturing whatever's outside of that 88%. You could do 1 minus 0.88 divided by 2. Or you could realize that, well, I'm not capturing 12%. And if I'm not capturing 12%, that must mean that there's 6% right there. And 6% down here. If that's 6% of the data, then this must be the 94th percentile. Z star would be inverse norm of 0.94, whatever that number is. And that would give you the particular Z star that you're looking for. If you were doing T, you would have to do inverse T of 0.94, comma, the degrees of freedom, and that would spit out your T star. Now, the TI-84 calculators come equipped with an inverse T. The TI-83 calculators do not. I have a separate video explaining how to do that, how to find inverse T if you don't have it on your calculator. There are multiple ways of getting that particular thing done. Now, one last little thing right here, just as a reminder in terms of formulas. Let's talk parameter. Let's talk statistic. Let's talk standard deviation. Let's talk standard error. This hopefully will be I probably didn't leave myself enough room. So you know what? Since I did leave myself enough room and I'm doing this live, I'm just going to crumple this paper up and do it again. Here we go. Let's do parameter. Let's do stat. I'll give myself more room for standard deviation and more room for standard error. Okay. Good. If you're dealing with proportions, you're using P. If you're dealing with a statistic, you got P hat. This is a population parameter. This is a sample statistic. If you're doing the standard deviation, it'd be PQ over N. That is assuming that you have the population P. If you don't have the population P, if you're trying to find the population P, this is mainly for intervals, then you would have to do standard error, which would be P hat Q hat over N with a giant square root. If you're dealing with the difference between the two of them, it's a difference of samples, or it's a two sample or something along those lines, then obviously these are pretty straightforward. But when you're doing a standard deviation, you cannot just combine them by subtraction. You would have to convert to variance. And not a typo, you would not subtract them, but you would add them. So you'd have to square it, square the second one, add them together, square root back. It's one of those problems where I don't bother trying to memorize this particular formula because it's not necessary. The reason why it's not necessary is because if you remember, oh, I just have to square the two standard deviations, add them together, and then square root them back based on the variance problem that we've done in the past, then you got it. The standard error would be the same. I'm not going to write it out. Same, but with P hat. Now, again, with the assumed mean with a test versus the trying to find the mean with the interval would determine whether or not you pool these things. But for the most part, pooling doesn't make too huge of a difference. It only really makes a difference when you are doing a multiple choice problem. But again, there's no multiple choice on this particular year's test. Parameter for mu would become x bar for the statistic, the standard deviation if you had sigma, if you had the population sigma, or if you didn't have the population sigma. The differences would be very similar. I'll just write those out here. If you were trying to find the two sample, depending on whether or not you have the samples there, of course, for the interval. But again, same concept. The standard deviation squared plus the other standard deviation squared, square root them back, which would be sigma 1 squared over n1 plus sigma 2 squared over n2 with a giant square root around them. Again, I don't bother to memorize this. Because I just know, oh, I square them, add them, square root them back. It'd be very similar right here, except instead of sigma, I would have S because I would have the sample standard deviation and not the population standard deviation. For matched pairs, you would have to find the average of the differences, and it's a very similar process. You would mostly have the calculator do that for you in terms of calculating the standard deviation. It depends on what you have. It's a very similar setup. Very, very similar setup. I'm going to scan all these pages. I know it was a lot of pages, but I'm going to scan all of them and make it in a shareable PDF link so that you can peruse and pick and choose whatever you feel that you need to memorize. Of course, there are more videos coming down the pike as we move forward.